So Bob gets out of this list. And we end up with two people, that is Alex and Carl, right? So that is a divide operation that basically says completed divided by puzzle list is the list of all names for which all people have completed all puzzles or essentially have an entry in puzzle list as well for each of the puzzle names. Any questions? So note, yes.
The person's name, it won't display the Bob who didn't finish all the puzzle, right?
Exactly, exactly.
Okay, thanks.
Yes. And note one thing, what is the resultant schema of my divide operation? So my input schemas are person name comma puzzle name divided by puzzle name, right? So this sort of is similar to your integer division. The common attributes between those two tables are not in your final schema. Your final schema is only going to have attributes that are not, that is in one but not in the other, similar to that set difference idea, right? So we would have a schema that is of person name because person name does not exist in this puzzle list here. Okay. So result relation context tuples completed that are evenly divided by puzzle name. So when I say evenly divided by puzzle name, I basically mean that for every tuple, there is an equivalent puzzle name in your puzzle list as well. So for Alex, Altecrew, Soma Cube, Altecrew, Soma Cube, and Puzzle Box exist. So Alex is a candidate for this particular division operation, but not Bob. Okay. So if that is the scenario, what is your divide operation doing? It is getting two possible schema relations. One is person name, puzzle name, and the other one is just puzzle name. It is going to compare these two relations and see that, okay, puzzle name and puzzle name are common across both of these relations. So I need to compare these two tables with respect to puzzle name. Right. So that also means that there has to be a certain subset of attributes in one table that are common in the second table as well. Right. So that is what this says, that S has to have a subset of attributes in R as well. And the resultant schema is going to be the difference between the two set of attributes. So R minus S. So here in this case, person name comma puzzle name is R. S is puzzle name. So R minus S gets us the attribute person. Right, so the resultant schema will only have person name. So that is the result schema is R minus S. And for every tuple T, we need to follow two conditions. And this might look complicated, but if you look at it, it should become quite obvious to you guys. So T has to be, the resultant tuple has to be an attribute that is within R minus S in your relation R. That is a projection down R minus S attributes. And for all TS in S, there has to be a TR in R. That is, for all attributes in my completed list, there has to be attribute in my puzzle list where TRS equals to TS of S. That is the common parts, that where S has the common parts across both of those things. And we get the list of all the person names equals to T, right? Okay. So every result in your division operation should have should satisfy these two conditions. Remember again that attributes in the completed schema, but not in the puzzle list schema, end up in your final list. So the division operation, once you get the hang of it, becomes a really useful tool. And essentially, I think we have a question like that in one of our upcoming first homework. At least I think in homework 2 as well. But essentially, once you get the hang of it, it should become quite obvious to you that this might look like somewhere I can apply division operations. Note that not all databases allow you the division operation. Some do, most don't. Again, this can be achieved using your fundamental operations as well, but that is something that we need to keep in mind. Okay. It is really needed, and it is easy enough to implement in the SQL if you really want it. Let's see what else. Yes, relation variables. So remember that that was division. So any questions about division before I move on? Tell me what would happen if, okay, so quick question then. If you don't have any questions, let me ask you a question. No, not you. Okay. So let's say that I have these two schemas, right? So let's say R is a schema that is basically, let's say, has three attributes, and I'm going to use the same thing. So person name, uh, puzzle name, and let's say that we have this another attribute in this completed list, that is maybe the version name of a particular person, or the version ID of a particular person, right? So let's say that we have version, right? And let's say we have this other table. mm, let's say that instead of version would make it a bit weird. Let's say the time it took to complete this particular person, right? So person name, puzzle name, and the time it took to complete a particular person. And we have a puzzle list relation that has, let's say, puzzle name. So if I perform R divided by, and I'm going to just type out divide here, but because it's notepad. So R divided by S. Can you tell me what is the resultant schema of this particular operation? That is the set of attributes that we would get. Yes.
Person name and time.
Person name and time. Exactly, right? Because we are removing all of the, you're correct. So we are removing all of the common attributes, and we just have the list of attributes for that are not common across both. Okay. On that note, what about puzzle name and version? If I had R is person name, puzzle name, time, S is puzzle name and version, what do I have as my schema? Again, it is going to compare across attributes that have the same name. So that is puzzle name, that is fine. We have person name and time, that was the first case. Main question is, does version exist in your final schema?
Yes.
Yes, right? I mean, because essentially what we are saying is, yes, because essentially what we are saying is all of, wait, not, yes, no, right? I mean, okay, so the resultant schema, remember, is always going to be R minus S. So if I perform R minus S or R set difference S between these two schemas, what is the result? I'm going to get all of the values in R that are not also in S. So I'm going to end up with person name and time. But since version is in S, we are not going to consider it at all, right? Because that is set difference. Does that make sense? Okay. Relation variables. So remember we talked about rename operations, that was row. And we said that renaming a particular variable renaming a particular operation does not create a new variable for you. It just renames it for future users, right? So we also have the ability to actually create relation variables if we want to, and we are going to call that as the assignment operation. So an assignment operations is quite simple. We are creating a new variable relva here. We have this left hand side arrow and e. So essentially we are assigning the values of e to a new variable relva. So this allows us to create results or relations from our table, and that can actually persist throughout your table. So basically that would now act as a new relation in your table as well. So we can say that temp1 equals, or temp1 left arrow pi r minus s r. So that creates a new project of those columns and then saves it into temp1, which can then be reused again in a later operation. And now temp1 would actually be persisting throughout your entire database. So you can reuse it again and again. Note that this is not the case in terms of rename operations, because a rename operation does not persist outside of your current operation. Okay. Yes. So I guess that's that about the assignment operation, and you guys can go through that as well. Let's start with relational algebra continued, so to speak. So we looked at select, project, set union, set difference, Cartesian product, and rename. We also looked at some additional operations that we could build on top of your fundamental operations, such as set intersection, natural join, division, and assignment, right? Well, assignment is not basically a fundamental operation, but we should have been, but anyway. Okay. So, well, the reason assignment is not a fundamental operation is because you can always concatenate all your operations together into a single operation, and that does not require any separate variables. And if you remember from your, I mean, if some of you have taken CS 410 programming paradigms or any other recursive programming course, remember that to solve a particular program, we don't need any more variables than the number of input variables. That is a proven theory, right? So essentially we should never want, or we should never need an assignment operator, but we don't care about that. Okay, now today we are going to move on to essentially more extensions to our operations, but mainly we are going to look into some aggregate and grouping functions that we can do, right? So essentially we are going to look at some mainly 6 aggregate or grouping operations that are basically standard as across most SQL implementations. We are going to talk about these 3 major extensions. That is, what is a generalized projection? We know what a projection is, but what is a generalized projection? And we are going to talk about aggregate functions and some more join operations. We talked about Cartesian product, that was just haphazardly combine all of them together. We also talked about natural join, that took into account the common attribute names across my tables and correlated that to get the final result. And we are also going to talk about some other join operations. So let's first talk about the generalized projection operation. So essentially it is the same thing as your project operation, but it allows you to perform certain operations on your values and create new columns for it if needed. So let's say that we had, let's talk about your previous, I don't think we have talked about this table yet, but let's say that we want to retrieve all credit accounts that have those account numbers and the available credit for each account. So let's say that our input schema has these 2 variables or 2 attributes, credit limit and current balance, right? And if we want to compute the available credit for a particular account, we just need to perform credit limit minus of credit balance, right? That would give you the actual arithmetic result for available credit. So this can be done using a project operation, where now instead of just allowing individual columns from your relation, we can also have some functions over those relations as well. So we can say f of j are arithmetic operations performed on certain